Welcome to a packet journey through PF. Let's start with the obligatory who am I? Who am I again? Oh yes, I'm Kristof, KP at FreeBSD.org. I've been a committer and basically the PF in FreeBSD maintainer since 2015. So everything that broke with it in the last decade is my fault. That all happens because I looked at what PF did at the time with IPv6 fragmentation, and I had the brilliant idea that, I think I can make this better. And I still haven't escaped. Since early 21, I've been basically maintaining PF full-time for pfSync, thanks to Netgate. I failed to bring the hat, otherwise I would have put the hat on. The actual introduction, where does this talk come from? It is shamelessly stolen from Alexander Bloom's talk, A Packet's Journey Through the OpenBSD Network Stack. He presented this at EuroBSD, YouTube link there. I'll give you all 2 seconds to write that down. It's a very good talk. It gives a good overview of how packets transit the OpenBSD network stack that turns out to mostly apply to FreeBSD as well. It is very nice to have that context for this talk. I found myself unable to squeeze a 40-minute talk in front of my 40-minute talk in a 40-minute slot. So we're just going to spend like 2 or 3 minutes looking at the FreeBSD network stack and where the firewall fits into that. Quick disclaimer about what we're going to be talking about. This is based on FreeBSD main as of today-ish, as of a couple of months ago. Some of the things I'll say here don't apply to stable 14 or stable 13. The concepts are broadly the same, but there's been a fair amount of refactoring, which is a polite way of saying code blatantly stolen from OpenBSD, but they haven't noticed yet that we stole it, so it's fine. Don't tell them. Anyway, the network stack. What happens, packets come in, device driver does magic, let's not get into what they all do, hand the packet over to Ethernet input. This of course assumes that it's an Ethernet packet, but the entire world is Ethernet. We can just forget that anything else exists. The Ether input function will demultiplex this because it could be an IPv4 packet, an IPv6 packet, it could be ARP, it could be spanning tree, it could be any number of things. Assuming that it's IP, it'll hand this to the IP input function, and then depending on what's contained within or where it needs to go, it'll forward the traffic or it'll terminate it locally in TCP and hand it over to the socket layer where hopefully an application will look at it and do something useful. The same thing happens on the way out, just in the reverse order. One of the things to remember here is that the order of operations for input packets versus output packets is inverted, of course. On an input packet, you handle Ethernet first, IP second. On an output packet, it's IP first, Ethernet second. So where does the firewall fit in? Well, right there. In FreeBSD, we have, because we love our users very much, we give them the choice of 3 different firewalls. So what we have is an abstraction layer in the network stack that says this is where we need to call into the firewall. That's called pfill or netpfill. And then depending on which firewall you have loaded, it'll dispatch to the correct firewall. You can actually set multiple firewalls. You're allowed, there's no law against this. Just know that my support policy for that situation is that I will point and laugh at you. There are people who do this. It sort of works for them. There are any number of things that will go wrong with this, hence the support policy. Just don't do it. Just pick a firewall and stick with it. IPFW is very nice. Slight simplification here is that I've only listed the pfill hooks in the IP layer here. There are also pfill hooks on the Ethernet layer, so you can do layer 2 filtering. IPFW does a great job of this. PF does a very basic job of this. We'll get to that later. Key concept for PF. PF is a stateful firewall, and the stateful bit really does matter. There is, of course, an exception. The layer 2 bits in PF are stateless, where we look at every packet individually without any further context. PF is stateful even for stateless protocols like UDP, because it turns out that in practice, while UDP is, stateless, for the vast majority of UDP traffic, DNS, you're going to see request-response. And PF will treat the response as being part of the same connection as the request. This makes writing your firewall rules a lot simpler. This means that you can write stricter rules. It is the 21st century. Do not accept stateless firewalls anymore. So we've got states. We also have rules. The rules are what policy are we going to apply to the packet or connection. Interesting thing, well, the important thing to remember here with PF is we process rules let me rephrase that. We always look for a state before we process rules. So if a state has been created for a connection, it doesn't matter what you do to your rule set, that connection will stay alive. We'll come back to that, I'm sure. Very high level overview. What happens, remember the network overview, packet comes in, it hits PF, it hits pfill, it gets handed off to PF. We enter PF in the PF test function. Strictly speaking, I've just lied to you. We actually enter PF check in or PF check 6 in, but those functions really don't do anything. The fun starts in PF test. PF test tests a packet. What does it do first? It sets up a packet descriptor, PF setup pdesk. This packet descriptor contains a bunch of context information for the packet. It helps us to avoid parsing and reparsing the packet. It remembers things like what interface did this packet come in on, where's the layer 3 header, where's the layer 4 header, what's the source address, what's the destination address, what was the source address before we applied the NAT transformation, stuff like that. So that's where we do most of the packet parsing. We also do packet normalization. That's PF speak for let's make this packet look the way we want it to look. The biggest operation there is reassembly, where if we have a fragmented packet, we wait until we have all of the fragments, we turn it back into the fragment it was, into the packet it was before fragmentation so that we can look at the full packet. This is important because you want to be able to filter based on the actual packet. And if you're fragmenting a packet, especially if you're a malicious user, you might fragment it in the middle of the TCP header, at which point we don't know what TCP port this packet belongs to, and you get to make a very difficult decision between, do I drop this packet and break fragmented packets for everyone, or do I accept the packet and then implicitly accept that anyone can bypass the firewall by just fragmenting their packets in a strategic location? Hence my motivation to do the IPv6 reassembly work. So we take fragments, we reassemble them, and then we continue processing on the fully reassembled packet. We'll come back to that in a little bit because that is relatively trivial for IPv4. There's some gotchas in IPv6. Anyway, we've reassembled the packet, so we have a nice big packet to look at, or it was not a fragmented packet in the first place. The next step is we PF test state, and then it's protocol specific. That has been unified a little bit. I believe these days it's PF test state or PF test state ICMP, because ICMP is very special. What does this do? It goes and looks for a state. Have we seen packets belonging to this connection before? If we've seen this before, if we find the state, we process the packet according to whatever we did, whatever we have stored in the state. So the same thing that we've done for other packets. If we don't find the state, that means this is a new connection, and presumably this is the first UDP packet for this connection, or it's a TCP SYN. We're going to do PF test rules, or test rule, which is we're going to process the rules and we're going to figure out what do we want to do in this particular case. Either way, either we found the state or we've processed the rules. We need to handle output. There are a number of things that we can do to packets. We can pass them unmolested and say, this is a good packet, I approve of this packet, it can go. We can throw it away. We can reject it, which is we throw the packet away, but we generate an ICMP error or a TCP reset so that the other side knows that this connection failed. We can route to, which is policy routing, which is where PF says, I know the routing table says the packet needs to go that way, but actually we're going to send it that way. This is in PFSync specifically used to do multi-WAN setups where you have multiple uplinks and then you want to bind your connections to a specific uplink, but you only have the one default route, of course. Finally, and this one is relatively new, is AF2, which is address family translation, which is NAT 6.4. So that's new in PF, well, new in FreeBSD PF. We took the OpenBSD code and ported it into FreeBSD. Along the way, found a very amusing bug that also affected OpenBSD. Happily has been fixed since. So in FreeBSD 15, you'll be able to do NAT 6.4. Or you can just install pfSync. Latest release has NAT 6.4. I promised I'd come back to IPv6, because IPv6 fragmentation is special. I'm sure some people here think, because it's a common misconception, that there is no fragmentation in IPv6. This is not strictly true. There is a difference in fragmentation between v4 and v6. You remember in v4, if a packet is too big, any intermediate router along the path to the destination can go, oh, this packet doesn't fit down my outbound interface, I'm going to fragment it and send the fragments onwards. v6 is different. In v6, the intermediate routers cannot fragment the packet. So if they get a packet that won't fit down the next hop, they generate an ICMP6 error, send that back to the sending host that, hey, your packet doesn't fit, try again. So you end up doing a path MTU discovery, and it is your sending host that will fragment the packets. It is only the receiving host that is supposed to reassemble them. But because of the discussion we've had, you really want to reassemble your packets to do proper filtering. We do reassemble them in PF, but then we're left with a big packet that potentially won't fit out the interface that we're trying to send it out. But also, if we reassemble and send it out that way, we're going to break the path MTU discovery. So what we do for while we're reassembling an IPv6 packet is we remember the size of the size of the largest fragment we saw, and then we reassemble based on that size. So there's a little gotcha there in the sense that if you have an interestingly fragmented packet, so your packet, you send 20 bytes, 20 bytes, 1,000 bytes, 20 bytes, 20 bytes. The way the packet looks, or the packets look on the way out, is it's going to be 1,000 bytes and then whatever's left over. Now that's theoretical, because in practice, all sane code that fragments packets is going to fill the MTU, and then only the last packet will be whatever's left over. So if you do that, it'll work just fine. If you don't do that, you might see strange things. So as we output the IPv6 packet, we look at the information that's associated with it that says, oh, we've reassembled this. This is the size we need to refragment to. We refragment the packet. We generate a whole bunch of new packets and output those. Second gotcha with that is that PF will actually call IP6 output or IP6 forward directly. So usually, if we go back to this, usually you will catch the packet here in the pfill hook, we'll gather them up, finally we'll reassemble, and the packet will continue its life through the network stack as a return from pfill. Rather for IPv6, when we're transmitting a refragmented packet, we're going to call IP6 forward or IP6 output directly. So the actual function flow is slightly different. And this is because the pfill hook understands the notion that it gets given a packet and it returns 0 or 1 packets. You can have no packet returned, we ate it, or we can have, here's your packet back, potentially modified. What it doesn't understand and what the calling functions don't understand is that you give 1 packet to pfill and it returns a whole chain of packets. So to bypass that problem, we end up calling IP6 output, IP6 forward directly. It's a lot of context here. There are some implications to how this behaves. Remember that we test for state first. I've already mentioned it. It means that we only evaluate rules if no state is found. So if you change the rules, say that you had a pass all policy, we set up a whole bunch of connections and then you apply new rules, you say block all of your existing connections will continue to function. Because the packet will come in, we'll do a state lookup, we'll find the existing state that says, yes, this packet is allowed, we'll apply that, and we'll just continue. We will never go look at the new block all rule. So if you want that behavior, you have to flush all of the existing states when you set new rules. Sometimes it's useful, but be aware that this is a thing. It can bite you, and I'm sure we've all been bitten by, here I've edited my rule set on this remote machine, I've applied them, and I can't connect to the machine anymore. I'm sure we've all done it, and if you haven't done it yet, you'll do it at some point. More implications of this. State lookup is incredibly important for PF performance, because for any given connection, we're only going to do rules evaluation for the first packet or maybe the first 2 packets. Everything after that is a state lookup and an output. So it is when you're benchmarking how many packets can I throw through this firewall per second, it's the state lookup that's important. So how does this work? And with this, again, a disclaimer, it is different on FreeBSD versus OpenBSD. On FreeBSD, we have a hash table. So we take the source and destination IP address, source and destination port, or for ICMP, type and code, the address family, and the protocol. And we hash this together, and we end up with a hash row, and we go and look in that row that is potentially a list of states. Do we find this state? So you can have multiple states in any given hash row. There are performance implications to this, of course. If you have many more states than you have hash rows, your lists on average will grow. And doing a linked list transition, of course, is a lot slower than doing a hash table lookup. So you always want your hash table size to be scaled somewhat reasonable given whatever state limit you want to implement. You're going to be okay if you have 2, 4, even 10 states in a row. It'll probably be okay. But if you have 1,000 times more states than you have rows, you're going to see your performance start to crater. There's a tunable for this, net.pf.states hash size, so you can't change that at runtime. You do need to reboot to apply it. If you set it too large, there are downsides. You're going to use more memory, but memory is cheap and I don't have to pay for your memory, so set that large enough. There are DTrace probe points that you can use to instrument how many states you have in any given row. That's the PF purge state row count probe point, and that gives you the row number and how many states it saw in that row. There's a cleanup process to delete expired states that will iterate through the hash table, and while it's doing this, it'll generate these probe entries. Another thing that is important for state limits is the way we implement this limit is we use a UMA zone and say you can never allocate more than X amount of items from this zone. That's fine and that works, but if you run close to the limit, you will end up with very, very slow allocations because Yuma has per CPU buckets of memory that is ready to hand out. And as long as there is memory in your per CPU bucket, the allocation is very quick. But once you start to get close to the limit, your local bucket is going to be empty and you're going to have to talk to other cores, and it ends up being quite painful to actually hit the limit. Moving on, control plane. So this is how we configure PF. This is not particularly interesting in and of itself. It's just this is how PF talks to the kernel. And right now there are three ways to do it. We've got the old ioctl style, which is all that OpenBSD does. And that's a fine approach to do it. It's where you copy a structure from user space into the kernel back and forth. And this works, and this is simple. And this is extremely painful if you change any of these structures. If you add a field, if you change the size of a field, all of a sudden user space and kernel space no longer agree, and you're in trouble. You can fix this by just telling user space, hey, recompile, and it'll be fine. The first attempt we had in FreeBSD to make this better is sticking NV lists. NV lists are name-value pairs, sticking those in the ioctl rather than a fixed structure, because then you can add fields without breaking compatibility between the kernel and user space. This is an improvement, but it is still a little bit annoying. The ioctl interface makes it really annoying to deal with the dynamic memory sizes that you need to make that work. And also NV lists don't perform particularly well. And this is fine for small commands, you know, add a rule, show me the list of rules, give me the status of PF, that's all fine. If you have bigger requests, like say, I want to export my PF state table that has 1 million entries, it is not fine, and it consumes all of the memory on your system, and it also takes forever. The third option is netlink. Yes, that netlink, the one you know from Linux. It's a socket that communicates user space to kernel space, or possibly kernel space to kernel space. It also has a type length value encoding, so it becomes easy to add fields to a request and it won't confuse the other side. It scales really well, so when I ported I didn't do the port. I'm blanking on the name. One of the Yandex people implemented netlink. And he also did the port to do the state export via netlink. And once we tweaked the user space a little bit to export 1 million states, instead of needing 4 gigabytes of memory, we needed 16 gigabytes of memory, and it was a little bit faster than the old ioctl style. So if you're a user, or if you are user space and you're trying to programmatically interact with PF, it's really annoying to have to deal with all three different methods. I would recommend strongly that you don't. There's a library, libpfctl, that implements many functions, not all yet. This conversion is in progress, rather. But if you have an application that programmatically interacts with PF, please, please, please don't try to implement the ioctls or netlink yourself. Use the library. If you're missing functions, tell me and we'll implement them. I have an aspiration to convert everything to netlink and then to get rid of the old ioctl interface. That isn't done yet, but if you use libpfctl, you don't have to worry about this. You just call a function and it'll do it for you and it'll be okay. So, you know, if you take nothing away from this talk, take this. If you're doing programmatic interaction with PF, use libpfctl. Don't write your own ioctl implementation because it will break and I won't feel sorry for you. We're talking about a kernel system, so we just cannot escape talking about locking. There are a couple of different locks in play for PF. There is a rules lock, which protects the rule set. This is a read-write lock, or rather a read-mostly lock. That is to say, you can have any number of cores at the same time, take the read lock and process rules at the same time without interrupting other cores. It's only when you modify rules that you need to take a write lock and that you're going to stop traffic on all cores while this is going on. I say read mostly because we have two types of read-write locks in FreeBSD. There is the read-write lock and the read-mostly lock. And the only difference between the two is that the read-mostly lock is optimized for read workloads, so where you have many more read locks than write locks. And that turned out to be relevant. Babak Farouki did the conversion of our read-write lock into a read-mostly lock, and we got a 65% improvement in packets per second for a mostly trivial patch to convert a lock type. So that was really nice to have, but slightly embarrassing. It took us that long to notice. He was actually trying to fix a NAT bug that was completely unrelated to the locking. He just accidentally gave us a 65% improvement in throughput. So I wasn't particularly upset with him. Especially not because he later built a test case to demonstrate his NAT problem, which enabled us to actually fix the NAT problem as well. We also have a state lock. So when we do a state lookup, we lock the hash row, which is another reason why you don't want too many states sharing a row, because you have the potential for multiple cores at the same time trying to lock states in the same row, and then you've got contention, and that's the enemy of your throughput, of course. So we lock per hash row, as I said. Another reason to make sure your table is well dimensioned. The state lock is a little bit interesting because I've kept things simple when talking about states, but it is, of course, more complicated than this. Because your state is based on your source IP address and port and protocol, and it turns out those can change. You can do NAT, you can do network address translation, you can change. This means that the IP addresses in the packet can be different on one side of PF versus the other side of PF. So what we do is we have two different states, state keys in the state tables that point to the same state. But you need to lock both hash rows in the state table to safely manipulate them. And of course, having to deal with two locks means that you have the potential for a lock order issue. If you've got two cores at the same time trying to deal with the same state, and one of them locks the first row first, and the other one locks the second row first, and then tries to get the other lock, you've got a classic deadlock, and those are not good. They're terrible for throughput. Great for security, though. So the way we solve this is that if we have to lock two different rows, we always lock the numerically lower one first, and that guarantees that we take the locks in the same order on all cores. And if you've got two cores trying to deal with the same state, at least they will both try to lock the same row first. So one of them is going to win and be able to make progress. The other one is going to contend on the lock until the first one is done, but at least it'll eventually make progress as well. There's more locking to talk about. PF users may be aware of PFSync. That is where we synchronize state information to another host. This is strictly a failover feature. Do not confuse PFSync for a performance feature, because you will be sad. What this does is every time that we update a state, it will send these updates off to the other host, which will reconstruct the state table so that if your primary host goes down, the other host can take over and have all of the state information, which means you don't have to drop any existing connections and your users are happy. It also means you can do firewall upgrades without impacting traffic too much. You're always going to lose some packets, but it's fine. It's just network packets. The problem here used to be that we had the nice and shiny clever locking in PF to make it all very fast, and then we'd enter PFSync, and the first thing PFSync would do is would take a mutex. So it doesn't matter how good we were in PF to run across multiple cores. The moment you loaded the PFSync module, you were stuck with single core performance. This makes people sad. So a few years ago, actually I'm looking at the commit back in 2018, I did some work for Orange to make this better. So what we do now is we split the PFSync updates into different buckets. Essentially, we map a whole bunch of states, state hash rows onto a single bucket and lock that bucket, which means that other states that are hopefully going to map to other buckets can proceed while this is going on. We've seen performance improvements 30 to 100%. You can tweak the number of buckets. My experiment showed that if you've got twice as many buckets as you have CPU cores, you get most of your performance without making things too much more difficult. And that is live in all current FreeBSD versions. As I said, it was done in 2018. You still pay a little. There's still performance overhead to running PFSync, which is why I say that this is not a performance feature. Don't think that you can balance load between multiple PF firewalls and synchronize them with PFSync and get them to work faster. It's not going to work. It'll be slower. Another shiny feature is somewhat recently PF grew basic layer 2 filtering. As I've mentioned before, this is entirely stateless, but we can do things like, Ether, because it's an Ethernet rule, pass protocol 806, so allow ARP packets. Allow all traffic from this MAC address and tag other packets, because these are quick rules, with the captive tag. The whole intent of this exercise was not to build a very capable layer 2 firewall, it was to enable captive portal features. So we're all familiar with the captive portal where you get to a hotel Wi-Fi and it's an open network, but you log on and they redirect you to a specific web page so you can give them money before they let you get to the internet. Or sometimes so they can give you a disclaimer before they let you. But anyway, we like to remember the MAC address of the host to do this, to say, okay, we've seen you before, you can log in and pass unmolested. But you need the MAC address, which we don't have in PF's layer 3 rules. So we do this in layer 2. We tag packets appropriately. You're allowed, you're not allowed. And then we can do the layer 3 actual complicated actions in there. Really mostly just want to point out that this exists. This is FreeBSD 15 only. Next one, SCTP, also an Orange project this. Those of you who don't know, think of SCTP as TCP, but with multiple flows embedded within it. It is the unholy love child of TCP and UDP. It supports multi-homing, which is why it's interesting for the firewall, because you don't just get the one connection where you set up a connection where it's very similar to TCP. It might also contain additional data that says, oh, by the way, I have this and this and this other IP address, and you can also talk to me on those. So what PF does is it looks at all of those packets. They're called ASConf chunks in SCTP speak. And based on the IP addresses that we see in there, we will create additional states. So that if you've connected from IP address A to B, and host A has said, I also have IP address C, and host B has said, I also have IP address D. We go and create states not just from A to B, but also C to B, C to E. Anyway, I'm losing track of my letters here, but we create all of the possible combinations of connections so that when those hosts decide to start speaking to each other using their other IP addresses, they will just pass through and all will be well. This is also unique to FreeBSD PF. I am not currently aware of any other open source firewall that handles SCP multihoming, which is why I mention it. I feel vaguely proud of this one. It hurt to get it to work, but it does work, so that's very nice. One more thing to talk about is counters, because it turns out to also matter for performance. So counters are where we count things, where we count how many packets and how many bytes any given rule or state has matched, possibly even for interfaces. And we used to do this, you had a uint64 somewhere and you just increment that number anytime that you hit it. And it's not necessarily obvious, but it turns out that this is terrible for your caching performance because you've got one core updating this and invalidating the cache line, and then another core tries to also update it, but you get memory accesses. Anytime that this core, any core touches it, you have to do memory accesses, and it is slow. There is a counter framework, counter 9 in the kernel that counts per CPU. So you keep a per core count of whatever you're trying to count, and it is only when user space asks for the total numbers that you go and look at every core and ask for their numbers, add them all up together, and you get your total. Advantage being performance. That's what these counters look like, or what they look like in the rules. That's all very nice. This is a relatively straightforward conversion to do. The biggest problem with it was that PF, coming from an OpenBSD side, tended to conflate the data structures, the structure definitions that it used for communication between user space and the kernel, and the data structures that it used internally to the kernel. Those were the same struct. So you can't change that struct in the kernel without affecting user space, which we don't want to do. So most of the work to convert this, these counters to use the counter 9 was splitting up those structures, doing the conversion between structure type, and only then could you make the change inside the kernel. This was another nice big performance improvement, and I think this is the one that pushed us to the point where, again, the last numbers I saw were from Olivier, were a few years ago, but at that point, IPFW and PF were basically tied for performance, right? If I'm remembering correctly, IPFW was still marginally faster, but it was very, very close. One more thing I want to point out is there's a bunch of static probe points in PF. Some of these are potentially really useful. We've mentioned the PF purge state row count, which means that you can monitor how many states you have in any given hash row. So that can be interesting if you're trying to diagnose performance problems, for instance. There's a probe point for ioctl errors, which is really handy if you're not sure why your ioctl call is failing. It can return the error number and a line number. There's some debugging probe points for SCTP when we're adding or removing multi-homed entries. There's probe points for when you're doing Route 2, and those probe points, I assure you, are there because I keep having to fix bugs with Route 2, Reply 2, Dub 2. Those are extremely useful to me. They may or may not be useful to the regular or average user, but they exist. There are more. As is always the case with DTrace, honestly, to make the most out of them, you really need to be looking at the source code to see what we're actually probing. There is also no stability guarantee of these, of course. This is all very specific to the kernel internals, and that's... I don't want to paint myself into a corner saying, this is how we're going to do it and nothing else. So they may change. I think I've covered everything here, so if there are questions, please feel free now. Questions, comments, complaints? Yes, we've got one person up there. I was told I wasn't allowed to throw it at you, so... Sorry. There we go.
Did you say netlink uses 4 times the memory than NVList when doing the memory state?
So netlink uses its own type length value encoding. It's conceptually similar to NVList, but it is not the same encoding.
Please, what is the performance gap between Netlink and NVList?
So the performance gap is there are basically two different advantages of Netlink over the NVList. The first is memory use. From the kernel to user space, Netlink can start sending data immediately. But with NVLists, we had to build the entire reply and copy the entire reply to user space in one go. That's where the memory improvement comes from. There's an actual CPU time improvement as well, and that is just purely because the NVList internal data structures don't scale well to very large lists. And again, this isn't really a criticism of NVLists, it's just a fact of life with them. If you use them for what they're intended for, they work just fine. It's when you start to abuse them for, I would like to return 1 million states, that things break down. Yep.
Okay. I think we tried loading 50,000 rules with NVList, and it took about 60 seconds.
Yeah.
And so, relatively, how long do you think Netlink would take? Like around 50,000
I
rules?
would expect Netlink to do significantly better. I can't really give you numbers there. What I can do after the talk is I can point you at my commit where I have some numbers for the state export. There's some timing information there. I don't know off the top of my head what the timing was. But also, 50,000 is quite a long way from 1 million. Of course, 50,000 is a lot for rules, but it is not a lot for states. Anyone else?
All right, so we got 4 questions from IRC. I guess we'll just let you answer as they come
Sure.
along. But first question from IRC, is the state hash table protected against hash collision attacks?
Yes, that is a good point. Yes, it is. At startup, PF will generate a random seed, and that seed gets stored into the hash table. So you would need to know that random seed to be able to deliberately provoke hash collisions.
Okay. All right, actually, we just got another question, so there's 4 more questions. Let's see here. Is there any documentation on writing Netlink generic services inside the FreeBSD kernel?
I'm not aware of any documentation. Best I can say is go look at the existing code. I don't think any specific documentation got written for that. Someone should do this. See one of our documentation people desperately diving for cover.
Okay. Does PF on FreeBSD support tables of MAC addresses for layer 2 filtering?
No, it does not currently support tables for MAC address filtering.
Okay. How many SCTP endpoint to endpoint combinations does PF track? Is this vulnerable to O(n)² state exhaustion attacks?
That is a very good point. I don't think we've actively considered this. So I think right now it is unlimited, and you could potentially exploit this.
Okay. And I think that's it so far. Are there any DTrace probe points users could use instead of PF log for debugging rule sets?
I was going to say there are probe points in the PF test rule function, but I'm not actually sure if I wound up committing those probe points or not. I'd have to go look at the code to tell you.
All right, and then there's that one last comment. Someone trademark should do this. Mwahahaha.
Yes. Tell this person I will find them. Going once, going twice. As far as I can tell, we've all survived this. I think that's a wonderful result.